Welcome back. This is Mrs. Hanson once again, going to wrap up our lessons in Chapter 1 with two remaining topics, the Vesper theory and intermolecular attractions. As we review the Vesper theory, we'll remember that it stands for the valence shell electron pair repulsion theory, the valence shell electron pair repulsion theory. In other words, we want to make sure that bond angles are maximized so that we are not sterically hindered in a molecular geometric shape. There are going to be review sessions here on the Vesper theory, and in your e-learning I have provided for you a Vesper chart that you may choose to print and kind of study over as you work to remember some of these geometric shapes. So when I talk about the Vesper theory and molecular geometry, we're remembering that the focus here on organic chemistry. So we're looking at really just 2, 3, or 4 electron domains. And sometimes electron domains can be referred to as a steric number, if that's a word that you might have heard of before. I use the terms electron domains. An electron domain from a central atom can either be a bond or a lone pair of electrons. So how many things are you looking out from a central atom? And the first I'd like to talk about is 4 electron domains in which all 4 of those electron domains are bonded and 0 are unbonded. And an example here might be a methane molecule, CH4. On a piece of paper, we're used to drawing methane, CH4, with what appears to be 90-degree bond angles by just creating a very, straight up and down kind of figure. We understand that that is not correct because we can maximize those bond angles by creating larger angles up to 109.5 degrees by altering the shape. If we place that central atom and have 3 of the 4 domains kind of pointing down, kind of like the base of a pyramid, and 1 pointing straight up, we have 109.5 degree bond angles in all directions. Clearly that is a maximized bond angles as if we pictured it instead of a 90 degree. So a tetrahedral molecular geometry where we have 4 electron domains leading out to all 4 of them being bonded to another atom. Carbon tetrachloride would be another example, CCl4, where we have the central atom has 4 electron domains in which all 4 are bonded, 0 are unbonded. 440 is how you would read your Vesper chart, finding it as a tetrahedral in shape. If we have, if we have 4 electron domains, but only 3 are bonded and 1 is unbonded, the shape is now referred to as a trigonal pyramidal shape. Trigonal pyramidal. For example, the molecule ammonia. Ammonia has a central atom of a nitrogen, leading down to 3 hydrogens, but instead of another atom up here, it has a lone pair of electrons. We would read this as 4 electron domains. Of the 4, 3 are bonded and 1 is unbonded. 4, 3, 1 on your Vesper chart. And remember, these electrons kind of are much larger. They're an electron cloud, if you will, and they end up kind of pushing those hydrogens closer together, somewhat, a little bit closer together. So you have an optimal bond angle that's actually less than than the previous slide, which was 109.5. Here you're seeing them at about 107 degrees. They slightly push together based on the density of this rich area of the electron cloud. So 107 degree bond angles with a trigonal pyramid geometry. If we have 4 electron domains, 2 of which are bonded and 2 are unbonded, as this example of a water molecule, 4, 2, 2 is how we would read that on the Vesper chart. You have what's called a molecular geometry of bent. Water is a bent molecule, 422, a polar molecule. And the bond angles are about 105 degrees, knowing that we have two electron-rich areas that are going to decrease the bond angle between these two hydrogens, just knowing that electrons take up more space, if you will. That electron cloud kind of needs more space, and it pushes the hydrogens a little bit closer together. So with 4 electron domains, we can have a tetrahedral if all are bonding. We can have a trigonal pyramidal if 3 are bonded. And we could have a bent shape if only 2 are bonded. Let's recall 3 electron domains in which all 3 are bonded. This is called trigonal planar. Just like an equilateral triangle, the equilateral triangle has the bonds leading out to 3 other atoms, and the bond angles between those is 120 degrees. The very important part of trigonal planar is that it is a very flat molecule. It lies within the same plane as the paper. And that's going to be very important when we talk about mechanism, if you will, especially when we do SN nucleophilic substitution reactions and elimination reactions. If we have a carbocation is electron deficient, meaning that it has only 3 bonds, missing one, making that carbon have a +1 formal charge. This is an example of a trigonal planar. And because it's flat, we can see that an attacking molecule could either come from the top side or from the bottom side. We can have an inversion or retention of configuration. So bond angles of 120 degrees, sp2 hybridization. Just as in before when we had tetrahedral, all of those tetrahedrals were sp3, 4 electron domains. Trigonal planar has 3 domains, so it's sp2 hybridized and lies flat in the same plane. A third characteristic of Vesper is a linear configuration in which we have simply 2 electron domains and all 2 are bonded. Here you can clearly see if this were Be and then hydrogen on each side, the bond angle would be a straight line of 180 degrees. A triple bond carbon is also an example of 180 degrees, not only between the 2 carbons, but also leading out to the next branch as well. So a linear geometry. And here's a chart that kind of summarizes what we've went through slide by slide. Noticing that we have, in terms of a steric number, I called electron domains. If I have 4 electron domains, all 4 are bonded, none are unbonded, we called that tetrahedral, bond angles of about 109.5. If we have 4 electron domains and only 3 are bonded, we called it trigonal pyramidal, and the bond angle is reduced slightly to about 107. If we have 4 electron domains and only 2 are bonded, leaving 2 lone pairs, we called it bent, and roughly about 105 for its degree of bond angle. Trigonal planar, we would have 3 electron domains all bonded, giving us a 120 degree equilateral triangle, and 220 gives us 180 degrees as well. And you'll be asked to practice determining bond angles and recognizing what type of molecular geometry around the central atom. So let's take a look at this example. Here's H3O+. This is what we called hydronium. It is the acid polyatomic ion H3O+. Does that look familiar from Bronsted-Lowry acid-base pairs? The central atom oxygen has 4 electron domains, 3 of which are bonded, and 1 is unbonded. Now don't let that positive charge bother you for counting domains. It's there to let you know oxygen has a formal charge of +1. Let's review that. Oxygen lives in group 6. It has 6 valence electrons. It has 1, 2, 3, 4, 5 assigned electrons, giving it a formal charge of +1. That's why you need to see the plus charge, because it's part of the Lewis dot structure. But it does not matter when we're counting domains. A domain is a bond. I don't care if the domain is a single, double, or triple, it still counts as one domain. And in this example, 3 are bonded, 1 unbonded. So according to your Vesper chart, 4 domains, 3 bonded, 1 unbonded is a trigonal pyramidal shape. So this is trigonal pyramidal. And that means the bond angles are approximately 107 degrees. Here we have a central atom of boron, and again, the negative charge is there because it has a formal charge. Boron lives in group 3, so it has 3 valence electrons. It has 4 assigned electrons around it, so that means it has a -1 formal charge. But we don't worry about that when we're counting domains. The boron here has 4 electron domains. All 4 are bonded, 0 unbonded. So on your Vesper chart, you read 440, and you see that that's tetrahedral. Bond angles of about 109.5. Around the central atom, we have 3 electron domains. All 3 are bonded, 0 are unbonded. 330 is trigonal planar. And here we have 440, 4 electron domains. All 4 are bonded. 440 is tetrahedral. Very significant in terms of organic chemistry, we discussed the carbocation with 3 domains. 330 is trigonal planar. And if the carbon ended up having a negative formal charge, notice here it has 4 domains, only 3 are bonded and 1 is unbonded. That's what we refer to as trigonal pyramidal. These bond angles are approximately 120 degrees, lying all in the same plane, whereas this carbon has a set of lone pair electrons, making the bond angle about 107 degrees. And the last major concept of our chapter is the polarity of molecules and intermolecular attractions. And based on the polarity, we can understand what type of attractions a molecule would have. Remember that a molecule is polar if it has unequal electron distribution. So for example, here is a carbon atom, and we clearly see the polarity of the bond is making the chlorine very electron rich. So this is a negative area, and the carbon's left with a net positive. The more negative region we can see, the more red it comes out in this diagram, and the more electron deficient comes out with blues. So this is what we refer to as a polar molecule, where we have an unequal distribution of charge. When I look at some examples, let's look at letter A. I have a molecule built of CH3 attached to a CH2, leading up to an oxygen and back down to a CH2, CH3, and I'll just draw those out. And I did that on purpose to give us a visual. Remember that the octet there of oxygen is requiring 2 sets of a lone pair of electrons. And so here, this is the polar bonds, right? So here I can clearly see that the electron density is being pulled towards the oxygen. This region of oxygen is very electron rich, and these carbons are electron deficient. This is what we refer to as a polar molecule. It has 2 polar bonds. And those polar bonds create an unequal distribution of electron charge. So it's overall polar. If I compare that to letter B, by the time I'm done drawing a carbon dioxide molecule, we have a double bond going to oxygen in either direction. Now these bonds are indeed polar, but notice that the dipole itself cancels. There is an equal distribution of electron charge. So the dipole moments cancel. And what that means is that I cannot point to any specific region in this molecule that's any more negative or positive. The bond is polar, but the molecule is non-polar because overall these dipoles have canceled, making the molecule very equal in electron distribution. It's a very symmetrical molecule. Non-polar molecules are always symmetrical. And just thinking about that, how the dipole moments canceled in carbon dioxide, but in this dimethyl ether, we had a very rich oxygen area, making the polarity stand out, where we had positive and negative regions in that same molecule. So just thinking about if a molecule is polar or nonpolar, think symmetry. Here is a carbon attached to 3 chlorines and 1 hydrogen. Clearly we can see this is not symmetrical, and what I mean by that is to be symmetrical, all 4 domains would have to be exactly the same, and they're not. So this electron distribution is being pulled away from the hydrogen and also away from the carbons towards all of the chlorines. So this is a polar molecule with very rich electron areas on the chlorine and electron deficient areas on the hydrogen and carbon. Here we have in letter B, CH3, O, CH3. And remember, when I think about the geometry, the oxygen has lone pairs of electrons. Sometimes drawing that out helps us see that. And I can see that the dipole moment is being pulled towards the oxygen, making it very rich in electron density. So this is also a polar molecule. NH3, when I draw its Lewis dot structure, I can see a very rich area here of electrons, making this very electron rich, and the hydrogen's very electron deficient. So this is a polar molecule. In terms of bond polarity, nitrogen, being the more electronegative element, is pulling the electron density towards itself and being pulled up towards the electron pair. And the last one, I have carbon attached to 2 chlorines, attached to 2 bromines. Clearly we see that these are polar bonds and they're being pulled towards the chlorines, towards the bromine, but this is not the same electronegativity. Chlorine and bromine are not the same. Chlorine is much more electronegative than a bromine. So this is a more dynamic pull towards the electrons as compared to this. So this is also a polar molecule. And I had drawn those out just to help emphasize where we see the vector arrow pointing to electron-rich areas and electron-deficient areas. You may certainly pause and make sure your drawings match these. Now that we understand polarity of molecules, we can apply that to the intermolecular forces and physical properties that accompany those polarity. So knowing that these properties, such as solubility, boiling point, density, states of matter, melting point, all of these things are affected by the attractions between molecules intermolecular forces are attractions between compounds, two molecules. Remember, neutral molecules, being polar and nonpolar, are attracted to one another. And we have three different types of intermolecular forces. And I'm going to abbreviate those, by the way, as IMF, intermolecular forces. The first being dispersion, the second being dipole-dipole, and the third being hydrogen bonding. And let's kind of review what each one of those IMFs talk about. The weakest is known as a London dispersion force, or simply dispersion force. So keep in mind that all molecules have kinetic energy. They are in constant random motion, and that means electrons in the molecule sometimes produce an electron distribution that's not evenly balanced with the positive charge in the nucleus. So a very, very temporary induced dipole will occur when two molecules become so close together they can influence the distribution of electron charge. The kicker here is to understand that it's so temporary. It's an instant in time, and then the electrons themselves redistribute to a non-polar configuration. But it's the interaction, the closer that two molecules become, where the positive charge on this particular nucleus, these are atoms, can influence the electron cloud of a neighboring atom. You can see closer they are, the more influential one molecule is on the other. So a dispersion force is a temporary induced dipole. All molecules can behave such as this. All molecules can exhibit dispersion forces. Now, a dispersion force can increase with increasing molar mass, larger surface areas. Now keep in mind, it's how we can influence one molecule to the next. So the longer the molecule is, the more surface area it has. The longer molecules means that it can interact over a greater surface area to create these temporary dipoles. If you have a shorter surface area, there is not as much area to interact to create these temporarily induced dipoles. So the longer the carbon chain, the heavier it is, the stronger the London dispersion forces are. The more energy it would take to raise the boiling point, right? Boiling points are affected by dispersion forces, meaning the heavier the molecule, the longer the molecule, the more energy it's going to take to force that liquid to turn to gas. So you can see increasing the molar mass, increasing the surface level has increased the boiling point. Now, if dispersion forces are influenced by the ability of a molecule to interact, we can have a greater surface area for interactions if we have straight chains. Right here, I just have 5 carbons in a row, all in a straight chain, plenty of opportunity to have a large surface area for interaction. But if I start branching, here I have the same number of carbons, but they're just attached in a branched form. Those molecules have less of a surface area, and they actually start to roll past each other and have a less of an opportunity to interact and set up temporary dipoles. And again, here's the same number of carbons, but this is just now one big giant ball of a molecule, right? It looks like a ball instead of a straight chain. These molecules are certainly going to roll past each other, having little opportunity to interact and set up dispersion forces. So low dispersion forces with high branching, high dispersion forces with straight chains. And you can see the higher the intermolecular attraction, the higher the boiling point. Butane or pentane, hexane, all these straight chain carbons can interact with one another through this large surface area and not roll past each other with those balls at the end of their chains. Now, a second intermolecular attraction is known as a dipole-dipole interaction. two polar molecules interact with each other to create very strong intermolecular attractions. This is a molecule kind of written up due to electron charge known as acetone. It has a central carbon atom leading out to a double bond oxygen. And we can see that the double bond oxygen makes this area very electron rich, and the carbon would be electron deficient, so positively charged. The negative region on one molecule is very attracted to the positive region on the second molecule. And these intermolecular attractions based on opposite charges are known as dipole-dipole. Now the difference is these are not temporary charges. That's the difference between the dispersion force, because it's just so temporary, where these are permanent based on the polarity of the structure. So polar molecules line up to create dipole-dipole interactions. Notice that these attractions are between the acetone molecule, and it's a much stronger interaction than the dispersion force. And a third and strongest of all intermolecular attraction is known as hydrogen bonding. This is a very special type and very strong type of dipole-dipole interaction. The hydrogen bonding is so attractive that it meets the criteria of being the strongest intermolecular attraction known. For example, if I have in a molecule an oxygen attached to a hydrogen, a nitrogen attached to a hydrogen, or a fluorine attached to a hydrogen, N, O, or F. Remember, these are the three most electronegative elements. If you see those attached to a hydrogen, which is not very electronegative, we set up a very strong intermolecular attraction. So between molecules, here's an OH, here's an OH. The hydrogen bond is between those two molecules. So the hydrogen of one attracted to the oxygen of the other. Here's an example of ammonia. Ammonia has an NH bond, and therefore the lone pair on the nitrogen, which is partially negative, is very attracted to the hydrogen, and this attraction here is known as a hydrogen bond. So this is the strongest intermolecular attraction, but it's very special in that the oxygen, nitrogen, or fluorine in the molecule must be attracted to attached to a hydrogen itself. So to apply these, we could practice by just asking ourselves which has the highest boiling point. And really to interpret that, we're asking which has the strongest intermolecular forces. So to do that, I'd like to just remind us what kinds of forces there are. So first of all molecules have dispersion forces. I don't care if they're polar or nonpolar, all molecules can align themselves to influence the electron distribution of the molecular compound. They're the weakest intermolecular attraction, but they all have them. Remember, dispersion forces are the only intermolecular attractions that nonpolar molecules have. It's the only one nonpolars have. This molecule is nonpolar. The central carbon is leading out to 4 identical methyl groups, CH3s. That is a completely equal electron distribution around the central atom. So the only intermolecular force neopentane contains is a dispersion. However, in this other molecule called 3-hexanol, 1, 2, on the third carbon, we see this hydroxyl group, OH. We know that this is a polar bond, and we know that this is a polar bond, making the oxygen very electron rich, the hydrogen electron deficient, and the carbon electron deficient. Those are partial positive signs on the carbon and on the hydrogen. So not only does this have dispersion, this means that it is a polar molecule, so it exhibits dipole-dipole interactions. And notice also that it meets the criteria for hydrogen bonding. It has an O attached to an H, so it exhibits hydrogen bonding as well. All three intermolecular attractions are present in 3-hexanol. The highest intermolecular attraction creates the highest boiling point, so therefore strong IMF means higher boiling point. Three-hexanol has a higher boiling point than neopentane. Let's try another. In this example, the central oxygen atom has a molecular geometry of 4 electron domains. 2 are bonded, 2 are not bonded. 4-2-2 means that it's a bent molecule. So think about that in terms of its geometry. Bent means that these R groups, these carbon groups, are really coming down at an angle of about 105 degrees, making this a very rich area of electrons, and the carbons themselves are electron deficient. So this exhibits dispersion forces because all molecules do. And since it is polar, it exhibits dipole-dipole interactions as well. It does not meet the criteria for hydrogen bonding, so 2 of the 3 are present here. In this compound, we still have the oxygen bonded to R groups. This R group contains 3 carbons. This R group contains 3 carbons. So did these over here. So we can see that this exhibits dispersion and dipole-dipole. So we need to consider other things. For instance, the larger the surface area, the greater the dispersion force can be to set up. Notice that this is a straight chain carbon. All in a row is a larger surface area for those molecules to interact. This is balled up. So since it's branched, those molecules have less of an opportunity to interact with one another. So therefore, the higher boiling point is the linear ether. That's the functional group here. This would be dipropyl ether, and therefore this would have the higher boiling point because it has the longer carbon chain on either side of the oxygen. Now in this example, we just talked about this particular molecule being an ether. So I have a bent structure around the oxygen, making this very electron rich. All molecules have dispersion. And this would also have dipole-dipole. Over here, this is polar, so I know that it has dispersion. It has dipole-dipole. And it also meets the criteria for hydrogen bonding. Since all 3 are present, these have greater intermolecular attractions, and therefore this molecule would have the highest boiling point. And that concludes our lessons from Chapter 1. It's time to go to work. Practicing, you have your Orion, a non-graded practice. You have your Wiley Plus assignment, which is a graded assignment. And finally, your proctored multiple choice quiz. Keep in mind you have learning assistant sessions to keep practicing with help, and I'm only an email away.